Hi, everyone. Thank you again for joining us for the Scaling CXL to Millions of Servers Vistara for Hyperscale Efficiency webinar. With that, I'll go ahead and hand it off to Neha to kick off the webinar.
Hello, everyone. Thanks for joining. We'll be presenting our work on deploying CXL at scale at Meta using Vistara, an end-to-end co-designed CXL solution. I'll start by describing why CXL was and continues to be a problem worth solving. First, 43% of the servers in our fleet today are memory-bound and not compute-bound. What this means is services running on millions of servers end up stunting precious resources like cores, memory, storage, because they ran out of memory capacity. And wasted resources translates into wasted dollars. Secondly, memory is the largest contributor to the carbon footprint in data centers. Specifically, 69% of the carbon footprint across all the components in the data center can be attributed to DIMMs. This makes DRAM our single largest sustainability lever in the fleet. And lastly, DRAM or memory has a much longer useful lifetime than servers. So typically servers retire or we retire systems around 5 to 7 years, whereas DRAM, on the other hand, has a much longer, specifically around 10 to 14 years of perfectly useful lifetime. What this means is every decommissioned server throws away several years of perfectly useful memory. And CXL offered a solution to address all three of these problems at once. We all know that CXL helps us decouple memory from the CPU socket. This allows us to land more memory capacity per server than what a typical CPU can support. And at the same time, it also helps us co-locate different generations of DRAM on the same server at the same time. So for example, we could buy new DDR5 memory or DDRN memory and also use some of the older DDRN-1 or DDR4 memory on the same host over CXL. However, it's been 6 years since CXL was first published, and there have been limited reports of CXL deployment at scale across millions of servers in production. The reason for this can be twofold. One is all the off-the-shelf components that have been available so far in the industry didn't fit the bill, that it didn't meet the requirements of the hyperscale deployment. And secondly, the software stack that needs to be run on top of CXL hardware was not ready to make it useful at scale in production. We also found that the reasons for this were more architectural than protocol level. So firstly, the CXL solutions or memory modules that were available at the time typically bundled new DRAM capacity with the CXL ASIC. What this meant was, in order to deploy CXL, we also had to buy new memory, which added to the cost and made the solution economically less viable at scale. Secondly, most of the CXL solutions didn't have DDR4 support, which meant we couldn't use our decommissioned DDR4 inventory with CXL ASIC and couldn't land the carbon wins or the cost wins as a result of that. And thirdly, notions such as the tiering software could have high overheads, high latency, or the CXL tail latency could be unstable, made CXL less lucrative from the perspective of deploying it at scale in production. So this motivated us to build Vistara, an end-to-end CXL stack, to help turn CXL spec into a production reality where we could deploy it across millions of servers and racks in the fleet. So we started by codifying our requirements for the CXL end-to-end solution with the objective of being able to deploy this solution at scale and maintain a fleet with CXL empowered servers. So the first requirement for the solution was to ensure that it is cost effective so that it's economically viable at scale. Second, we wanted to ensure that we could use our decommissioned DDR4 inventory to be able to lower the carbon footprint as well as help us with the cost effectiveness. Third, since we had to deploy CXL across hundreds of thousands of services, we had to prioritize ease of adoption. We couldn't have possibly asked services to rewrite their code to adopt CXL. So we had to make sure that it was offered transparently to services without them having to treat it as a special purpose memory. Fourth, we wanted the solution to be generic and broad such that once it's open sourced, wider community can go and use it and leverage it across a broader range of use cases. And lastly, we are introducing a new hardware component in the fleet. Typically, this requires us to have robust tooling and maintenance flows to ensure that we can monitor its health across the fleet, across millions of servers, and take action if there is there are any issues that arise in the fleet. So we had to ensure that the solution has low operational overheads and maintenance flows are sustainable. So with these objectives in mind, we designed the end-to-end CXL stack using Vistara ASIC, using hardware software co-design. So at the lowest level, we have the Vistara CXL ASIC, which is a custom ASIC designed with power and cost efficiency in mind. And we ensured that Vistara could be used with DDR4 memory technology. On top of that, we have MemServer, which is our 1 terabyte memory optimized server platform. It has 2 Vistara ASICs per server. And the objective here is to be able to offer a high memory to compute ratio to services that are memory bound that can then fully scale up and better utilize the standard resources such as CPU, storage, network bandwidth. And on top of this hardware, we also designed the software stack with the primary objective of hiding the complexity of adopting CXL from the applications, as well as like keeping tooling and maintenance flows as simplified as possible. And we have this stack today running in production across several services across hundreds of thousands of servers. So next, let's talk about the 1 terabyte server. The server has a 158 core AMD Turin processor. This processor has 12 memory channels. Each channel supports 64 gigabytes of DDR5 DIMMs. And then on top of that, we have 2 Vistara ASICs per server, which allows us to populate 256 gigabytes of CXL memory. With this, we are able to collectively offer a 1 terabyte of memory capacity with a 3:1 local to CXL memory ratio. So typically for memory capacity bound workloads that are candidates for this server type, we've observed that not all of the memory that's allocated by a service is utilized all the time, and we'll provide more data on this in upcoming slides. Typically, it's a small subset of pages that are hot and frequently accessed, whereas the rest of the memory is cold and infrequently accessed. And we've observed that our total hot footprint across all the services in the fleet typically ranges between 20 to 30% of the workload's memory allocation. So with this, 3:1 local to CXL memory ratio suffices for us to keep the hot memory in the local, and cold memory can then spill into CXL. Next, let's talk about the Vistara ASIC. We have 2 of these ASICs on each of the servers. Each ASIC can be connected to the server using by 16 PCI Gen 5 lanes. However, we end up using only 8 per ASIC in production. And then on the memory interface side, we have two DDR4 channels. Each can support 2 DIMMs per channel, which gives us a total of 4 DDR4 channels on the CXL side. So the reduced PCIe lanes being used, as well as the 4 DDR4 channel decision, was primarily driven by the fact that we don't expect to drive high bandwidth over CXL because we primarily use it to host colder pages that don't drive very high bandwidth. And we use our decommissioned DDR4 DIMMs that operate at 2400 megatransfers per second. We have 4 of 32 gigabyte DIMMs connected to CXL ASICs. This allows us to drive a peak bandwidth of 48 gigabytes per second over CXL. Now let's talk about latency. The idle latency for CXL is around 250 nanoseconds. And if we talk about the loaded latency under production operating conditions, because we end up driving very high bandwidth over local memory channels, we end up operating at the higher end of the latency bandwidth spectrum, typically around 60% bandwidth utilization, which drives higher latency of around 230 nanoseconds. Whereas on the CXL side, we end up driving very low bandwidth, and hence we end up operating on the lower end of the latency bandwidth spectrum. As a result of that, the latency gap between local and CXL memory is in the range of 50 nanoseconds, which is not perceptible from the workload's perspective, and hence we don't see any unexpected anomalous performance degradation for workloads when we introduce CXL memory in the fleet. Lastly, the total power consumption for ASICs as well as DIMMs is in the range of 50 watts. There were several design decisions that went into the ASIC design that ensured that we don't over provision and keep the power in perspective when we design Vistara ASICs, which helps us keep our power footprint sustainable. With this, we have two Vistara ASICs per 1 terabyte server, and then we have the server design that we talked about. And on top of that, we run the software stack to hide the complexity of using Vistara in the fleet. So we'll next talk about the software side of things. And with that, I'll hand over the presentation to Hassan.
Hello. Thanks, Neha, so for providing the details about like how why Vistara is needed and what is the hardware configurations and what is the like very basic. Let me share the screen. Okay. So thanks for like providing very high level idea of like these Vistara's hardware stack and why Vistara is needed. Now I'm going to like focus on like what is the software stack we need to like these end-to-end CXL enable in our million server scale server fleet. So we want to make things as transparent as possible because like applications they don't want to change their service providers, they don't want to change their applications. So a transparent OS mechanism solution is the like way we wanted to like provide for the Vistara. So in our system, like the CXL memory is directly connected to the CPU. We make it appear to the OS as a separate NUMA node. So why this allows us to maintain a distinct boundary between like local memory and the CXL memory, and we can this boundary allows us to like manage memory across different tiers based on their latency, bandwidth characteristics, and also at the same time, we can actually leverage the standard OS virtualizations and other memory management mechanisms from there. So here, instead of like relying on the BIOS to make CXL appear as a system RAM, we deferred the mechanism to our Linux driver. We build our custom Linux driver that basically expose the CXL memory as a zone movable node. So why zone movable? Because if it was a like zone normal mode, then our system pages or the kernel pages or the pages that could not get migrated later on, they could appear to the CXL and that could be like stuck there. So just simply a simple mechanism of like making a CXL node as a zone movable gives us the safeguard to like critical pages, system pages, those are very frequently being used or those are very important. They could be like always stick to the local. We don't want our system pages stuck to the CXL and those system pages is making our applications life miserable. So just like making it zone movable, make the CXL node zone movable, mark it, and you can actually get rid of like systems memory spilling into like the CXL node. And for the configurations or the discovery of the CXL, we are relying on the like ACPI table, like the CXL's early discovery table that describes the configuration of the CXL memory to our Linux driver. And from there on, we can actually know like this is the address ranges where CXL memory is residing, and from the HMatch table we know like what is the bandwidth characteristics, what is the latency characteristics of this particular node, and that helps us our Linux kernel or the driver to decide on like what characteristics I should care about a particular tier, and based on that how I can actually move pages or manage pages across different tiers. So this is how we actually bring up the CXL to our system. And next comes like how we are managing memory across these tiers. So for this, we use a OS component, Transparent Page Placement Policy or TPP, which has been published in S Plus 2023. It has been like presented so many times and already become an industry standard for tiered memory management. So I'm not going a deep dive into it, but I'm giving a very high level idea of how TPP works and what is the philosophy of TPP for memory tiering management. So we, by default, our OS try to allocate pages to our local node, and our application is completely or completely unaware whether it is running on a CXL enabled systems or a normal system. It is. I'm running on some systems. It doesn't have to care about like what systems it is running. TPP is basically making the memory management across multiple tiers for the applications. So as long as I'm finding enough memory in my local node, our CPU is allocating memory pages to the local node. It is allocating memory pages to the local node until the node is full. So when the node is full, that means I need to make some spaces for my hot pages to stay there. So why hot and cold things? Because like the hot pages are the most critical pages of an applications of a workload. So we want to keep as much as hot pages to my local node because the local node has the like fastest memory tier. They are the lowest access latency. So as much as of my hot fractions of an application is served from the local node, they will get like premium benefit out of that. And we will only serve the cold pages. Cold pages means the pages that has been very infrequently accessed or they has been accessed within a very long time. After a long time, I'm going to access. They are not frequent. So they can actually reset in the CXL. Infrequent access to CXL, they might have like extra 50 to 100 nanoseconds of extra latency. And then we will demote our cold pages to the CXL, stay there, and make space for our hot pages to serve from the local node. So this is the demotion mechanism involved in the TPP. When you are filled up in your local node, initiate demotion, and the demotion is a basic migrations. We don't use swapping or other expensive operations here. So just the cost of like page migrations or a copy of a page from local node to the CXL node. Now for a application, some pages which is like hot, they can be cold, and the cold pages can become hot again. And we, as I said, we don't want to like serve hot pages from the CXL. So when a page is hot, become page resetting the CXL, become hot again, we promote it back to the local node so that we always try to optimize our local node to serve as much as hot pages we can. And for these things, we utilize the NUMA balancing or auto-NUMA mechanisms. There, we actually sample pages over the CXL nodes and After certain sample time, if something we poison a bit of the pages, and when those pages has been accessed, it creates a like hint fault. From the hint, we actually decide on, okay, this is hot enough, and we should actually promote it back. So this is the high level idea of like how TPP works. And while working on this mechanism, we find certain page allocation policies can help for certain applications with certain behavior. For example, for some applications which are very page cache heavy, they actually allocate the page caches at the very beginning of their journey, beginning of the allocation mechanisms of the work of the applications, and later they never use those page caches. So keeping them in the local node for an infinite amount of time and then demoting them, that actually not optimized enough. So what we decided, we found, okay, directly allocate them in the CXL node. This is a one-touch allocations and one-touch usage. So directly allocate them to the CXL node and later forget about them, or you can get rid of them from the CXL node. So just page cache allocated to the CXL. This can help certain types of workloads. And another types of policy could be like weighted interleave. What is weighted interleave? Right now, the interleave mechanism is like you allocate one on local and another on the CXL node, 1:1. So in a scenario where your CXL node is, let's say 4x lower bandwidth drawing, a 1:1 interleaving might be very hurtful. You are wasting your resources. So there, and weighted interleave, let's say 4 pages on local and then 1 pages on the CXL, I can optimize both of the bandwidth of the both memory nodes. So there could be like many other special allocation policy for special applications, and those are optional. Those are not mandatory part of them. In whatever application you need, you can actually use those allocation policy, and those could be configured from the OS level. So this is one way of demoting cold pages from local to CXL. Besides that, we use another proactive mechanism, TMU. TMU means like transparent memory offloading. This is another SPLOS 2022 paper. So here what we do, TPP demote pages in the critical path. You are full, and then you are basically demoting pages. And TMO helps as a proactive demotion. So even before we are struck, like we are hitting the node full, we try to find a point where we can actually reclaim more or demote more cold pages to the CXL. So how it works? So it has like two components. One is like the user space tool, Senpai, and another is like a kernel space monitoring mechanisms. So what do we monitor? We monitor the pressure of um, resources. So when we run multiple containers, if they are out of some resources, let's say like memory resources or CPU cycles or storage resources, Senpai monitors them through some PSI informations. So through the PSI or special stall informations, we measure how much of how much of an applications or a container is suffering because of like lack of resources. It could be I am out of memory, I'm having too many page faults. So to serve the page faults, my CPU cycle is wasting time for really or for more meaningful application serving. So it is wasting time to serve the pages, not doing any meaningful application cycle operations. So those PSI stall information is collected in the kernel level, and then we feed it to our user space tool Senpai. From those information, Senpai actually decides on, okay, this container might be under pressure. Let's say like it is struggling way too much to serving the page fault. So I might, this container 1 or 2, it can be like it should need to free some memory so that like it can actually its hot pages could be served instantaneously from there. So from that point, it decide which containers needs to like reclaim more, which container needs to like demote more pages to the next tier, and then it actually asks the memory reclaimer, hey, do this amount of like reclamation on these particular containers, and the rate of reclamation, how much amount of memory I need to reclaim or demote to like the CXL tier. This is defined in the runtime based on like the system's real-time behavior. So the pipeline of the reclamations, if it is the containers running memory on the local memory node, then go to the CXL. So if it is out of the CXL memory node, then go to the storage. So it is a one layer TPP. When local memory node is full, you're demoting to the CXL, and another layer TMO. It is always monitoring all the containers, how much pressure under it is going through, and based on the pressure, it is actually propagating or flowing the cold page movement across different tiers. And in our fleet, we actually decide to like make it uniform throughout wherever it is CXL is there. It is 1 TB uniform server as of today. And in those server, I have both local and CXL populated, 786 gigs of like local and 256 gigs of like CXL, uniform to my whole fleet. And whether a service wants to opt in or opt out, that is decided in the service launch time. So it's not like we are deciding in the BIOS level, hey, we are enable it in the BIOS and everything running on have to be CXL. No, we allow the service to choose, I want to run on CXL or not. In the same server, if service A comes and they wants to like, hey, I want to opt in, then you can actually, okay, go with like both local and CXL. And at the same time, if some service don't want, they can just run on the local memory. So how we are actually managing those things, we are implementing or we are deciding those things from the C group level. So in the C group, CPU set.mems, you can actually decide which is the memory zones or which is the memory nodes I want to, which memory nodes I want to execute on. So if I include the CXL memory node there, then okay, I will run on both. Otherwise, like you can actually decide on which nodes you actually run from there. And this has to be like, this can be like decided in the job launch time. So once a service launched without opting out of the CXL in the next launch, if it wants to decide to like use CXL, it can actually change its parameter and have the benefit of the CXL. So we no need to like BIOS changes or any reboots of the systems to like opt in or opt out. You can actually simply restart your applications or your service and have the benefit or opt out of the benefit. And while we're actually running on these things, we also monitor the health of our systems. We also collect like what is the resource usage, CPU resource utilizations, memory utilizations, the network utilizations, how much bandwidth going to the CXL versus on our local memory. So we collect all the metrics, and that helps us. We continuously monitor everything, and that helps us to like decide debugging or decides on how performant our system is, whether we are lagging behind on somewhere, where we are struggling somewhere, whether we need to like make things optimized or not. So it's a continuous monitoring of the performance, continuous monitoring of the like any issues or any sort of like things happening in the CXL world. In the fleet where CXL is running, we actually continuously monitor them and we decide on like what to do based on that health or levels or error levels, or we need to like update any BIOS or any frameworks. We decide based on our like fleet-wise monitoring systems. And now I'm going to give you some idea what is the behavior local versus CXL in our production. So as I said, like we enable like capacity local on 768 gigs, CXL is 256 gigs. And for that, we can actually collect the bandwidth of like 614 gigabytes per second on the like local side. On the CXL side, like the peak bandwidth should be like 76 gigabytes of bandwidth. The effective bandwidth we can get is like around 52 Gbps. For that, we need to, the power we draw is like 30 watt. 30 watt for the DIMMs, memory DIMMs collected, 30 watt for the DIMMs enabled on the Vistara. Each of the Vistara ASICs, they add another extra 9 watt. So 9 plus 9 is 18 plus like this 30 in total, it's around like 50 watt completely. Just if I consider only the memory's power is like 30 gigawatt. And if I say like what is the per gigabyte power, just enabling extra 256 gigs of CXL, we are basically we are basically 30% less power consuming. And in terms of like cost, we are basically saving 87% of our cost per gigabyte. So this is much cost efficient, also power efficient. And if I think of like the latency, what is the latency of the CXL? That is a very common questions in the throughout the last 4 or 5 years. CXL is consuming way too much of latency. What is the latency here? Uh, the ideal latency of CXL is like 250 nanoseconds. The more bandwidth you drop from the CXL links, the latency will shoot up. So if I say like, okay, I want to like utilize 10% of like CXL bandwidth, available CXL bandwidth, the latency goes to like 269 nanoseconds. And if I utilize, let's say 60% of my CXL bandwidth, the latency can shoot up to like 370 nanoseconds. And we optimize our CXL utilizations in a way, like let's say I'm running a workload that is like utilizing 80% of the total bandwidth. Then I will try to break it down 60% running on the local, 20% of the bandwidth getting on the CXL side. So in that case, my 60% local running latency, 60% of the bandwidth that is running from the local, it is like 234 nanoseconds. And if I utilize only 20% of CXL bandwidth, it will give me like 284 nanosecond kind of things. So we are basically like adding extra 50 nanoseconds if we split the usage 60% on local, 20% on CXL kind of things. So there is definitely trade-off. Like if you consume all the bandwidth on the CXL, your tail latency will be higher. But if we know, if we regulate, okay, this is the way I want to like utilize between local versus CXL, spill my workload in a particular way, then you are basically staying within a very reasonable boundary of like latency. And now comes like what types of workload we will actually offload to the CXL. That actually depends way a lot on what is the hotness behavior of the workload. So what is hotness behavior? You have a memory, every applications when they runs, they allocate lots of memory. Not all the memories are always being fully accessed. Some memory is always being accessed, some may be accessed after a certain time, and some may be like, okay, I allocated once and I am reaccessing in very later time. So if I break the whole workloads memory address range, if I make the percentile, what percentile of my footprint is how many times of hot? Let's say like 100 gigs of like workload. Uh, so that is, if I have 100 gigs of workload, not all the 100 gigs is basically always being access. Like for here, one of the use cases like for ads, I can see like 25% of my workload is basically accessed within 22 seconds. So this 25% of my memory footprint is always hot. So I should be very careful about what I do with them. And then if I increase the footprint or increase the fraction of memory, then I can see my P50 is not that hot. In the in the 50th percentile, memory gets reaccessed in once in 30 minutes. If I go even further, my 75 percentile is even much colder. In once in an hour, it gets accessed. And going to like P99, even more colder. In 2 hours, I can get an access there. So here, what only matters, my P25, where I am putting my P25, that only matters. For the rest of them, I have enough headroom in terms of the latency. Even if they go to the CXL, I can bring them back anytime. And that 15 nanosecond is not that significant enough here. So if I profile some other workloads for cache, here you can see like even P25 is much colder. It's like 4.3 minutes, even in the P25, 25 percentile case. Some cases like web one, like P55, P50, 50 percentile is also very hot. Within 2 minutes, I'm getting one access. 75 is some headrooms, and P99 I have more headrooms. And like here web 2, this is also the same story. So this behavior of the workloads, when you profile its memory access heat map, and you can get an idea what fraction of memory I can actually keep to local versus what fraction of memory is safe to put to the CXL. So from our empirical analysis across the whole fleet, we found like P75, 3:1 ratio is a good enough. Keeping it's very conservative enough to keep my hot frame mostly on the local, and CXL will mostly have my cold footprint. And that's the way of like a very Barca level view, which application is good for CXL and which I should like keep on which tier, and how much of them should remain in a particular tier. So high level idea, if your workloads have very large cold memory, or in other sense, like very high idle time, CXL tiers extra latency does not impact much to your applications. So with all of this, we are running CXL into our millions of servers fleet for quite a while. It has been deployed for years, and it is running production services for quite a long of time. And we find it is basically helping us. It is helping us for ML parameter of servers. With CXL, I'm having larger memory. That means I have like now I need less amount of servers to serve larger models. With CXL, we could enable like 100 terabytes of like model that they could actually run without like with less fan out. And this reduces our this ML parameter server with the help of CXL reduces the server count by 25%. And for cache applications with bigger memory footprint in a single server, that means I can serve more cache from my single server. I don't need to go to my storage pretty often. And as I'm serving them from my local memory, I can reduce the query processing time had been reduced by 30%, and that improved my throughput also. I can get a like 25% of throughput increase. And with CXL, also here, my fleet size is reducing. The total number of extra servers is reducing because a single server can provide me more memory now. And the development infrastructure is like the stuffs we are building, our developers in Meta, what they're working on, they need to like build, compile stuffs. With CXL, more memory available, you can actually fit more containers or more workers within a single servers, and you can run things more parallel. And that also helps the reducing the fleet size. And for data warehousing, we run like Spark, Hive, or Costco, those kind of things. Now they can actually pack more of their executor within a single host. That means less out of memory conditions happening for these executors. They can execute more stuffs in parallel, the execution time reduced. And for these types of workload, we can see a 30% reductions in the total server count with CXL. Just adding more memory helps for these kind of cases. So with server count reduction and reuse of our DRAM, like repurposing our older DIMMs, we can actually reduce the carbon footprint, and also we can actually reduce the total TCO of our fleet. So of the last 4 or 5 years, while we're running things into the productionizing the CXL, we have learned a lots of stories. We have learned a lots of experienced a lots of things. And if I summarize those experiences, we find like a stable 270 to like 370 nanoseconds of CXL latency is good for most of our production, a good wide range of our production workloads. So there is a myth of like CXL is a very high tail latency, and that tail latency is like destroying everything. We saw a different story. We said, yeah, tail latency is there, but if we configure in a particular way, in a more intelligent way, those tail latency is not harming you. Rather, we can actually tame the tail latency. And the workload impact, the way you are actually dividing like 3:1 or 60:20 bandwidth speed, that actually decide how much extra latency I'm going to gain from local versus CXL, 50 to 100 extra latency gap between local and CXL. This is meaningful, but again, like these with better page placement, better memory management, this extra latency is not harmful for your applications. You can actually sustain those latency for a wide range of applications. And there are could be like many complicated way of like enabling tiering. You can actually have completely redesign your OS, or you could have like completely very fancy user space tools for enabling tiering. That works fine, but in our cases, we found a simple OS-based tiering works. TPP works. With TMO, it performs even better. And we found this simple tool, simple mechanisms is not causing you too much overhead. Only the extra CPU overhead is within 0.5%. So simple thing make things work. And for hotness detection, we can rely on hardware counters. You can do many other stuffs. But so far, the OS LRU-based hotness mechanism that is there forever, that can work, and that hot working set identification with the 3:1 setup, this is working for our large fleet, wide range of workloads. And with that, I'm going to like end my talk. So to summarize what we did, we had Vistara, our in-house ASIC. This is the first work that reported CXL deployment at scale, where millions of servers are basically running on CXL. And we find our custom ASIC design with transparent operating systems and built-in production scale, production grade software tools that is good enough to make CXL enable in world's one of the largest fleet data center. And with CXL, we can definitely gain applications performance benefit. We reduced our fleet size, we reduced the carbon footprint, and it is a huge TCO win for us. And I feel like this is the start of the CXL journey. It's not end of that. We are just starting with the CXL, and there are many, many things have to become in the CXL area. And that's all from me. If you have any questions, me and Neha, we are ready to answer them.
Excellent. Thank you, Hassan and Neha, for that great presentation. First question from and yeah, if you have any questions, please do drop them in the Q&A box at the bottom of your screen and we can get to them as we go through them. Our first question is, what is next for CXL?
Neha, if you want to answer.
Yeah. So with Vistara, we deployed first generation CXL in the fleet with select memory capacity bound workloads, and now we are scaling it across the wider fleet. So we are looking for more use cases in terms of services that can benefit from CXL. Secondly, like the primary use case for this generation of CXL was memory capacity expansion. We are also looking at other use cases where we could do more with the CXL ASIC that we are landing in the fleet. If there are bandwidth expansion use cases that could leverage the additional DDR channels that we are putting behind the device, that could be another use case to look into. We are looking at what we could do on the device side to make it more performant and power efficient. Also, there are like other widespread use cases that industry is looking at, such as now that we have this ASIC in the fleet, can we put some compute on the ASIC to see if we can leverage the silicon that we are putting closer to memory. And then there are like standard use cases that the wider industry is looking into, such as pooling, sharing. So yeah, it's going to be an interesting roadmap.
Excellent. Thank you, Neha. Let's see, another question from the chat. Is your CXL device a PCIe card, and are there two ASIC on one by 16 PCIe card?
We have two Vistara ASICs. Each of them has a by 16 lane interface to the host. However, there are 2x8 connectors. So each of them are independently connected to the host. Um, I hope that answers the question.
Great. Then the next question, does MemServer share memory to other servers? If yes, then how? Is it on the network?
No, in this generation, we are not doing sharing. So each server has a dedicated CXL solution. So each server has dedicated to Vistara ASIC-based CXL uh, memory attached to it.
Okay, great. The next question is Vistara CXL 2.0 or CXL 3.x? And can you talk a little bit about how interoperability is achieved with CXL hosts?
So Vistara is a 2.0 ASIC. I think in terms of um, uh, yeah, I'm not sure about the second part of the question. Um, we can maybe get back to you guys
Yeah,
later on that.
that's good. One question here. What is the future roadmap looking like for this product?
So as Neha said, like we are thinking of like many there could be like many opportunities over here. Like CXL, we enable okay memory capacity expansion works. Next, what extra we can actually get out of these particular chips? Like as maybe we are still exploring many possible options. There could be like okay these have like as this is like 6XL 2.0 with 6XL 3.0 and 4.0, there will be like many ventures or many features will be available to the CXL domain, and also this compute or some other in the silicons what extra features we can actually get out of that. So we are still exploring. It's like wide open stuff for us also. Yeah.
Excellent. Great. Then our next question is, do you see value in having a pool local to several servers to keep a warm cache for web workloads when VMs and containers have to migrate?
So in our cases, like pooling can be definitely yeah one way of moving forward, but that also depends on like what are the workloads you are trying to do. So these VMs or web workloads we are using, this basic CXL, this is serving for us for now. So maybe like in next generation, yeah, it can help. But for now, I think like the way we are actually doing the CX good enough for us.
Okay, great. The next question, is there anything specific in Vistara that helps with the TPP or NUMA tiering, or is this coming from the standard CXL protocol?
No, for TPP and tiering, we are entirely relying on the software stack, specifically the like you mentioned, the TPP and other like declination and NUMA balancing algorithms that are part of the upstream kernel.
Yeah, so Vistara is Vistara is our own ASICs, and TPP on all the software stack that we build, those are all like open source, like in the Linux, within the Linux. So they will work with or without Vistara. Those are generic enough for running on anywhere.
Excellent. Let's
So the
see.
question is like how TMO decides which page to demote, and does it also perform proactive promotion? If yes, how it decide the pages to promote? So the in both of the cases, TPP or TMO, the demotion path we rely on like OS generic reclamation mechanism, the case of the or direct reclamation, those kind of things. It's just like we are notifying, hey, we are triggering, hey, we need to like demote something. That's the way. And no, TMA does not do like the promotion stuff. For the promotion, where you have to like rely on the TPP. The TPP is page promoting stuff that is doing the promotion, not the TMA. TMA is just like reclaiming pages.
Great. Let's jump to this question. Do you think CHMU will be used in the next generation?
So hardware level hotness monitoring, like yeah, like right now we are relying on like the autonoma for the hotness for the promotion mechanisms. A hardware level or like in the CXL level, a hotness monitoring that will definitely help us like to have more decided information about like the what is the hot trapped in the CXL instead of like relying in the like NUMA info or something. So there's definitely some potential of these things, and yeah, this could be a good addition maybe.
Okay, great. And then the next question, have you modeled the TCO impact of purchasing the DDR4, DDR5 memory instead of leveraging reuse?
Neha, do you want to comment on that?
Yeah. Yes. So there are a couple of benefits of reusing DDR4. First of all, like we had a bunch of inventory from the prior servers that we were decommissioning that we wanted to use. And with reuse, we also get the benefit of reducing the overall carbon embodied footprint. So that was one of the primary motivators. And also like it's almost free memory if we try to use the decommissioned inventory, right? So that was one of the primary requirements for the solution. But yes, like we always do the TCO analysis when we design a solution for various aspects beyond just reuse versus buy. So yes, like this was part of the evaluation.
Excellent. Next question, what is the role of or value of compression in your use cases?
So with compression behind the device, we can definitely add more capacity to the box and help memory capacity bound workloads to scale up better and better utilize resources. However, um, compression is not free. So we need to evaluate the latency impact as well as the bandwidth amplification impact of compression to, evaluate how it would impact our workloads and what are the solution, what is the solution space for us to offer compression transparently to the services in the fleet. So
Excellent. The next question, the presentation primarily focused on the capacity expansion use case of CXL. Could you talk a little bit about the bandwidth expansion case?
do you want to take that, Hassan?
I'm fine if you want.
So far, in the first generation of CXL, we primarily targeted capacity bound use cases that um, tend to have a very small hot working set. And as a result of that, they end up drawing very high bandwidth over that small subset of pages. And over the wider capacity, memory capacity that these workloads are located, we didn't have a use case where we ran out of the bandwidth provided by the CPU socket. So, however, there could be like more use cases beyond the ones that we have targeted so far that could benefit from bandwidth expansion. So, like I said earlier, like this is one of the things we would like to take a look at and see if CXL would help us there.
Excellent. And kind of in that same vein, are there any workloads that performed poorly with CXL, and what steps can be taken to make CXL work for them?
So as I said, like if we think of like those hotness memory access behavior, like okay, some workload that has like pretty much hot all the time. So in that cases, if you like try to look feed them into the CXL, definitely you will have like extra latency. Like because like your memory might be like thrashing, like most of the workload is hot. And also like if you have the workload has like very high bandwidth drawing from the CXL with more bandwidth over the link, your latency will shoot up. So that is also a poor workload that is not running over there. So there could be like many ways, like maybe like optimizing those workloads in a way, or trying some other mechanisms like the, yeah, instead of like just hot cold movement, you might need to think of like the other ways of like putting them to the CXL. So those are, yeah, those are opens for us to like even figure out. And yeah.
Excellent. The next question is a follow-up. So a follow-up on pooling. Assuming that link latencies improve for CXL from where they are now, would you consider keeping LLM KV caches in a pool for machines useful, or is the domain decomposition of workloads to servers also okay for now?
So like the KV cache, the way they're increasing their yeah, they could be a very good use case for the pooling. And CXL being a cheaper memory that have might have like more potential for hosting KV caches over there. Um, but like whether this is, which one is okay for now? Yeah, I think like that's the like subjective things, like which one is okay for now. Like the like if you think of like the bandwidth perspective, like the bandwidth right now we're serving on the CXL side, it is like with 2 ASICs it's like 76 gigs at the peak. The effective could be like around something 50 Gbps. So that bandwidth could be a bottleneck over here. But if we have like multiple if we add multiple CXL cards in the system, then you can might have like some additive bandwidth there. It could be hosting the KV cache could be one way of moving. Yeah.
Okay, great. And then we only have time for one more question. So in the case of the latency tail, when bandwidth utilization is high, did you investigate if DDR5 would have helped with that?
So we didn't look at the tail latency stability as well as variation, as well as the bandwidth versus latency curve. And we found that like the loaded latency for CXL and the variation that we see in the loaded latency over CXL um, is comparable to the trend that we also see on the local memory side. So even though like for CXL has higher absolute latency, but as we increase the load, as we see the loaded latency ramp up, we didn't find anomalies where we saw like tail latency being abnormally high with DDR4 compared to other DDR4 data that we have from the fleet or from the DDR5 based data from the MemServer's host attached local memory.
Excellent. Well, I believe that was the last question that we had time for today. So thank you so much to our speakers, and thank you for everyone for joining today. If you'd like to view the webinar on demand, the video will be made available to view on the CXL Consortium YouTube channel, and the presentation will also be added to the CXL Consortium website. Thank you all for joining.
Thank you.
Thank you, guys.